Euclid's Elements, Book 3, Proposition 36. If a point be taken outside a circle and from that point two lines, straight lines, fall on the circle, one touching the circle and another cutting the circle, then the rectangle contained by the line cutting the circle, together with the straight line intercepted outside it between the point and the convex surface, that rectangle will be equal to the square on the tangent. So here's our situation. We have a circle, we have a point outside the circle, call this D, and we have two lines, one touching the circle and the other cutting the circle. Now, this cutting line, DA, is either going to go through the center or it's not. So the first thing we're going to talk about where the cutting line that goes through the center. So let's have our center be E. And so here's what we're going to prove. We're going to prove that the rectangle contained by AD, DC, is equal to the square on the tangent, the touching line, DB. So the first thing we're going to do is we're going to draw a line from the center to the point of contact of the tangent line, the touching line. And we know from Book 3, Prop 18, that when we connect a line from the center to the point of contact of a touching line, it will contact that tangent line at a perpendicular angle. So angle DBE is a right angle. Now we can invoke Book 2, Prop 6, which tells us that when we have a line that's bisected, and this is bisected, the radii, and a piece is added onto it from the outside, that the rectangle contained by ADDC plus the square CE, that will be equal to the square on DE. So go back to Book 2, Prop 6 to review that. And what we should be able to notice here is that the square on CE, which is a radius, is going to be equal to the square on BE. So we can replace the square on CE with the square on BE. So let's rewrite that. ADDC, rectangle, plus the square on BE is equal to the square on DE. But the square on DE is the hypotenuse of this right triangle DBE. And so we can rewrite the square on DE as the sum of the legs. So we can write that this is actually equal to the square on BE plus the square on DE. Oh, sorry, let's see, the square on DB. And this is according to Book 1, Prop 47, the Pythagorean theorem. So the square on the hypotenuse is equal to the sum of the square on the legs. Therefore, we're just going to replace the square on the hypotenuse with the square on BE plus the square on DB. So now we rewrite this and we say ADDC plus the square on BE is equal to the square on BE plus the square on DB. And we should be able to see that we've got two equal terms on both sides of this equation. So if we remove equals from equals, the remainders are equal. And what remains is what we're trying to prove. Namely that ADDC is equal to the square on DB. So this is the case where the cutting line goes through the center, and it either goes through the center or it doesn't. And so the second case we want to consider is where it doesn't go through the center. So here it does and here it doesn't. It doesn't go through center. So our picture will look a little different. Our picture will look like this. And we'll have our line here. And so here is our touching line, and then here is our cutting line. And in this case, it's not going to go through the center. So let our center here be E, and DA is not going to go through it. So let's have C here. And the first thing we want to do is create, as we did before, we want to invoke book 3, Prop 18. And that tells us if we draw a line from the center to the point of contact, it will contact that tangent line at a right angle. So angle DBE, as before, is a right angle. Also from the center, we can drop a line, we can draw a line from the center to a line not through the center, and what will happen is it will contact that line at a right angle, and it will also bisect it. So that's according to Prop 3 of Book 3. So we have another right angle here, angle E, let's call this F, angle EFD is also a right angle. Now let's connect some points here. Let's connect CE and let's connect DE. And so what we see here, we have a series of right triangles. And at this point, we're going to do the same thing we did here. We're going to invoke book 2, Prop 6, that tells us when we have a line that's bisected and a piece added on beside it, that the combination of ADDC plus the square on CF is equal to the square on DF. Now, CF is a leg of this right triangle. So let's add the other leg. Let's add EF. Let's add the square on EF to both sides. That preserves our equality. And what we should be able to see is if we take CF and add FE, that's the legs of a right triangle, and that's going to equal the square on the hypotenuse. So this is going to equal the square on CE. And DF, EF, FE, that's the legs of this green right triangle, and that's going to equal the square on DE. So we can rewrite this. ADDC plus the square on CE is equal to the square on DE. And this is, of course, using our Pythagorean theorem. We can use our Pythagorean theorem one more time to see that the square on DE is the square on the hypotenuse of this triangle, so we can resolve DE into the square EB and the square DB. So this is the square on DB plus the square on EB. And we can note that CE is a radius and EB is a radius, therefore the square on CE is actually the same as the square on EB. So we can rewrite this as the square on EB. So now we have ADDC plus the square on EB is equal to the square on DB plus the square on EB. Again, we used Prop 47. We can see here, hopefully, that we have two terms in common. We have the square on EB on both sides, so we can remove equals from equals and the remainders are equal. And what remains is what we're trying to prove. That the square, so this is again what we're trying to prove, it's the same thing as here, is that the square ADDC is equal to the square on DB. And that's what we have. The remainder ADDC is equal to the square on, DB. This is equal to this. And that is what we're trying to prove, that the rectangle contained by the whole of the straight line, AD, plus the piece intercepted on the outside between the point and the convex circumference, so ADDC is equal to the square on DB. And we've proved that whether it goes through the center or whether it doesn't. Therefore, we can conclude QED.